Okay, so today we want to go over a little bit about osmosis. We've talked about simple diffusion and facilitated diffusion. Both of these are types of passive transport processes. They don't require any ATP. Osmosis is basically the same thing. The only difference is it's the diffusion of water, which is a little bit different because it's polar. But the thing that's got working for it is it's very small. So even though we've said polar things have trouble getting through the membrane, water is the exception to that rule because it's so small it can actually find pores and special proteins that enable it to get through the membrane pretty much whenever it wants. So osmosis is the diffusion of water from high to low, and this sets up a condition called tonicity. This is kind of a new word maybe for you, but basically all it is the relative concentration, how much of something we have, of solute, and we'll talk about that word here in a second, inside versus outside the cell. So how much of something we have inside versus outside the cell is called its tonicity. Now, if you're not familiar with the word solute, solute refers to dissolved material. Now, this could be ions, it could be carbs, it could be proteins, it could be sugar, it could be anything that we've put into a liquid and created a solution. So over here on the left, we have solutes, which tend to be solid. We have solvents, which tend to be liquid, and if we put those two things together, you end up with a solution. So if I had salt and water, we'd get salt water. Okay, so that's kind of how that works. The solute is really what we're paying attention to because that's going to determine the tonicity. Okay, let's look at, there's three situations. The first is called isotonic. And isotonic, the prefix iso means same. So in this case, we have an equal concentration of solute inside and outside of the cell. So it's equal solute on both sides. Okay, well let's look at how this would work by going to a little diagram. So you can just kind of do a sketch of this in your notes. You could do just a rough sketch of a beaker and some sort of cell inside. This is kind of like our dialysis tube lab that we did. And we've got some sort of solution on the outside, we've got some sort of solution on the inside, and on the inside we've picked a 0.9% salt solution, just a little bit salt, but most of it's water, and that's what we really are going to be paying attention to. On the outside of the beaker, if this is indeed isotonic, iso was equal, what percent of salt would I need to have outside the cell? Well, this one's pretty easy. It has to be the same. So if I have 0.9% salt dissolved inside the cell, if this solution outside the cell is isotonic, I have to have the same value. Okay? So that's isotonic. Well, that also means we have the same concentration of water. Now, in this case, salt is polar, so salt can't go through the membrane. So I've got all this salt floating around outside the cell. I've also got some salt floating around inside the cell, but it can't go anywhere. So even if it did want to come in, it's going to just bounce right off. It can't get through. But the water molecules can go through. Okay, it's small, even though it's polar, water molecules can easily pass through the membrane. So in this case, I've got the same amount of water on both sides. So if some water happens to move in, some water has to move out at the same rate. So this cell is going to be normal. It's not going to change its shape. Water's going in, water's also coming out at about the same rate. Okay. Well, that's isotonic. That's what you want to happen. Let's look at a second situation, which is quite a bit different. This is called hypertonic. Hypertonic, if we look at the definition of this one, hyper means greater. So you think of somebody who's really hyper, they have lots of energy, and that would kind of help you maybe remember what this means. We have a greater amount of solute outside the cell. We have a higher concentration of dissolved material outside the cell. Well, let's see why this is a problem. Let's get rid of some of this. Okay, so where we're back to our regular picture, you can make another sketch. We still have 0.9% salt inside, but this time we want to make the outside hypertonic. Well, hyper's greater. What would be a value of salt greater than that? You could have come up with anything. Anything higher than 0.9 would be hypertonic. So in this case, we've got 3% salt. It's saltier outside the cell, is all that's really saying. Now the reason that's important is, if it's 3% salt, that means there's only 97% water, just to add up to 100%. There's more salt, that means there's less water concentration. Okay? Now, we've already said salt can't go through, but water can. Look at where there is more water. Is there more water in the cell, or is there more water out of the cell? Hopefully you notice there's more water in. 99.1 is higher than 97. The way osmosis works, water will always go from high concentration to low. Well, in this case, the high concentration is inside. The low concentration is outside. I'm going to see, in this case, water leaving the cell faster than it's coming back in. If I've got this cell with water pouring out of it faster than it's going back in, what will happen to its shape? This cell will shrink. Okay, it's kind of like a balloon. It's lost a balloon that's got holes in it. It's losing its shape. It's going to shrink smaller and smaller and smaller as more and more water leaves. We call this crenation. Okay, it's going to crinkle, is kind of the way I think of it. It's going to shrink. Okay, that's not what we want. That's hypertonic. Okay, that's a bad setup. Let's look at a third situation. Hypotonic. Hypo is low. Hyper is greater. Hypo is low. Okay, that'll help you remember. Lower amount of solute outside the cell. Hypotonic solutions have a lower amount of solute outside the cell. All right, let's go to our diagram. Get rid of some of this stuff. This time, let's make it hypotonic. Hypo, low. Well, right now, man, that's 0.9% salt. That's pretty low already. Let's make it really dramatic. No salt, just water. This is something called distilled water. Nothing in there but just water, okay? Salt can't go through. Where is there more water this time? 100 versus 99.1. Okay. Water wants to go from high to low. There's more water outside than inside. So what you're going to see in this case is water entering the cell faster than it's leaving. What will happen to the size of this cell? It's going to expand and eventually possibly get to the point where it would burst. And this is called hemolysis. Okay, hemolysis is where the condition where the red blood cells could expand to the point that they actually would burst under the pressure. Okay, that's not a good situation either. The way osmosis works is the water will always go from high concentration to low concentration. All right, let's look at one animation that might kind of help pull some of these ideas together. Let me make it a little bit bigger so you guys can see it. Okay. So at this point, red line here in the middle is going to represent a cell membrane. And notice what the water's doing. Water's moving through the membrane back and forth. It is at equilibrium. Now let's add some salt. Okay, if you notice, when we added the salt, some water molecules stuck. Okay, water stuck to that salt. Okay, that's why it dissolved. When that happened, there was less water just freely floating around that wasn't attached. And what had to happen, if you notice, let me go back and play it again. When that water attached, some of the water on the other side moved over to try to balance it out. And if you notice, there is now a higher amount of water on this side. This is hypertonic. This is hypotonic. Okay? All right, hopefully that helps.